All right, so we have an isothermal silicon chip of width 20 millimeters on one side soldered to an aluminum heat sink, where that heat sink has a thermal conductivity of 180 meters Kelvin. So I think what I'm going to do is I'm going to kind of zoom in on my picture here because I kind of made it a little bit prettier, and then I'll continue to read through the problem. All right. So we've got a width on one side. So that's this guy right here. That's given to us. And then we're given some other parameters. We're given the K value of our heat sink, which I've put right here on the right, of 180 watts per meter Kelvin, of the same width. The heat sink has a base thickness of LB 3 millimeters. So that's this guy right here. So that's this little distance right here. And an array of rectangular fins. Each one is 15 millimeters long. So I've drawn that in pink. Airflow at 20 degrees with a heat transfer coefficient of 100 watts per meter squared Kelvin. And then we have a fin thickness, so I've drawn that as T, of 0.182. The solder joint has a thermal resistance of, and it's up here on the right. So I'm going to zoom in on this, but essentially there's a contact resistance where those two pieces are joined together. So there's a resistance to flow. And if you remember, we had when we defined those conductive or those resistances, thermal resistances to heat transfer, the units were in Kelvin per watt or degrees Celsius per watt. And you can see here, they've given it into us in meters squared Kelvin per watt. And they've got these little two hash marks there. So if I want to get it in the terms that I'm wanting it to be in, I'm going to go ahead and divide it through by the area. And it's going to be that whole area there in kind of orangish. One thing that's not given to you while this guy is given to you, that width, they don't actually give you the other portion of it. They don't give you what this is. It ends up being 20 millimeters as well. And the reason is you need to calculate it. So there's 11 fins. Hopefully you can see that behind my head, but there's 11 fins. I know it's not drawn like that in the picture, but there are 11 fins. I guess this is just a section of it. So you have n minus 1 times this parameter s, which is not also, that wasn't given in your problem statement, so I put that on there. But the S is just the spacing between those fins. And so it would be, you have n minus 1 of those spacings. So, and by the way, oops, it's the spacing between this point and this point. So it would be 10 of those times that spacing, and then you have that little bit extra over here, which is T, and that's how you would calculate the width up at the top there. All right, and again, that width up at the top ends up being 20 millimeters as well. So now that you have that, you could put the thermal resistance to heat transfer, because of that little contact junction, you could put that in terms of Kelvin per watt by dividing that 2 times 10 to the negative 6 meters squared Kelvin per watt by the area being 20 millimeters times 20 millimeters. So you've got to put it in meters squared, obviously, but I end up getting, let's see, I've got a value of 0. Oops. I've got 0.005. That's going to be Kelvin per watt. Okay, so I think I've sort of got all my ducks in a row as far as, what I'm going to do next, or at least all my parameters. I think I have most everything that I need. They also tell me that that chip is, that top chip there is 85 degrees Celsius is isothermal, so that is what it is. And it says, so it says if the maximum allowable chip temperature is 85 degrees Celsius, what's the corresponding value of the chip power QC? So essentially, I'm looking for Q of the entire array. What's it pulling off of there? Um, it does say an adiabatic fin tip condition may be assumed, so we won't need to use a corrected length or anything like that. And then airflow along the outer surfaces of the heat sink may be assumed to provide a convection coefficient equivalent to that associated with airflow through the channels. So that's just kind of, we talked about that in, I believe, the first video um, for fins, because since the flow characteristics through those fins is going to be different than the flow characteristics like on top of the fins or around them, since those flow characteristics would be different, your heat transfer, your convective heat transfer coefficient would also be different. But we're just saying, no, it's just 100 watts per meter squared Kelvin. We're not taking into consideration those changes. All right, so need to find Q. Perfect. And so I'm going to make some assumptions here, I think. So first thing I'm going to assume, let's make this a little bit bigger. I'm going to assume one-dimensional, steady state Q dot within the medium that I'm talking about is 0. And so I think I'm going to start by putting together a little thermal circuit. And so I'm going to start with the temperature of the chip. That's going to be the first one. So again, this is TC, and that was my 85 degrees Celsius. Then I've got a little thermal resistance here. All right, so the first one is going to be RTC. Right, so if I look right here, this is right here, that's where the temperature is 85 degrees Celsius. And then of course, I've got some thermal resistance due to that contact there. So that's going to be, we calculated that thermal resistance to be 0.005 Kelvin per watt. So we'll go ahead and put that on there. 0.005 Kelvin per watt. All right, so that's due to the that contact resistance. And then let's see, so the next temperature is just going to be the temperature at the base. So I'll just put a little TB there, but maybe I don't really need anything, right? TB, the temperature right there, that's the temperature at the base. And actually I do need, before, because that's not actually the temperature at the base, actually. That's the temperature at the bottom of that little connection. But I also have a thermal resistance right through that little section right there, don't I? So I'm actually going to put him in purple because it's the resistance through that LB, through that 3 millimeters. So the thermal resistance would be what, L over K? And it's L over L over Ka, right? So L over A. And then the next one that I need to do is the one through the fins. So this guy right here is actually my base temperature. And then the very last temperature is going to be the temperature of that air. So 20 degrees Celsius. It's my T infinity. There we go. And so let's see. So this one's going to be, yep. So this is going to be, and then that thermal resistance is going to be the theta B over Q total. And so if you want to go look at our, where that is, let's see where that is. Yeah. There you go. So that's us talking about the array. And then I can get that value. This is that one right there as well. So, okay, so that's 1 over the efficiency of the array times the convective heat transfer coefficient times AT. So, okay, so let's put that in there. Actually, let's, before we do that, let's at least get our Q, because this is our governing equation. So the Q that we're looking for, that QC from the chip, here's our QC. So that's going to be, I got to sum up all of these resistances. But I'll have 0.005, and this is Kelvin per watt, plus, and then I've got the thermal resistance, thermal resistance through this little 3 millimeter kind of chunk. Let's get that. So I have 0.003 meters. And then my thermal conductivity, what was he? Thermal conductivity was 180 watts per meter Kelvin. And then the area, well, it's just that the area of that big square right there, which is, we look at it, that's 20 millimeters times 20 millimeters, so 0.02 times 0.02. Come on. So 0.02 meters squared. Okay, so that's it for that one. And then I got to add up the next one. So that theta B over QT, we do actually have another equation for that. Yes, it's theta B over QT, but it's also 1 over the efficiency of the array times H times A total. So let's put that on there. I'll write it in those terms. So I have 1 over efficiency times H times, what was it again? Times H times, my goodness, times the total area. All right. So I think I can maybe handle some of these one at a time. Oh, and I think I want to add those temperatures at the top. So it's going to be 85 degrees Celsius minus our 20 degrees. Okay. So let's go ahead and at least get the area, the total area. I think that'll be the easiest. Maybe I'll say where. All right, so total area. I put this in blue here. All right, so the total area is all the area that I give this thing for heat transfer. And so it's going to be, well, it's going to be the number of fins, and this is off of your equation sheet, the number of fins times the area of each one of those fins. Okay, plus the area of that exposed base. So that AB, and that area of the exposed base, let's go ahead and get that as well. So this is N times AF. The exposed base, if I look at my figure up here, that's these areas right there. And so you can see that's going to be, well, if I took the entire area and then I subtracted the cross-sectional area that each of those fins are covering up, that would get me that exposed base area. So this is going to be plus the W squared, right? The total area. Actually, I won't put W. I'll just put, this is just area, right? Where this guy right here is W squared. Minus the number of fins times the cross-sectional area. Okay. So it'd be really nice if I had a value of that. So the total area ends up being, and I'll go ahead, I know there's a lot of digits, but just so we can avoid as much round off error as possible. So I end up getting 0.00695,996. I know that's way, way, way more than I need, but just so we can, like I said, avoid some of that round off error. So that takes care of the total area. H is given to me, and now I need to figure out what the efficiency of the array is. So let's figure that out. All right. So it's defined as the total total heat transfer rate over, I guess I'm going to call this QT max, and that would be if the entire thing was, the entire array were at the base temperature 85 degrees. And we do have an equation for this guy. Let's see. So it's this guy right here. And I've got this equation, but I also have this equation right here. So I think I'm going to use that second one that I boxed there. So yeah, so 1 minus, I have to look back, I think. Probably. 1 minus in the number of fins times the area of an individual fin over the total area times 1 minus the efficiency of a single fin. And by the way, the area of an individual fin in this case, so we've got these rectangular fins. So the area, well, we can calculate the area of the entire fin. So if I think about it, so I've got the area through which heat transfer takes place. It's going to be like along that area right there. So the area of my fin would be that LF times W, right? It would be N number of fins times that LF, the one that I had drawn kind of in pink on my diagram, times W. Oops. So let's look at that again, right? So this guy right here is LF, this guy right here is W, and of course I've got it on both sides, so I need to take that into consideration. So that would be times 2. Okay. Alrighty, and so I've got an area of, for this guy, I end up getting actually 0.00695 0.0006. So really I mean, like the hardest part about these problems is figuring out what the areas are. It's the most annoying part. All right, so I've got in my equation over here, I've got N, I've got AF, I've got AT. The only thing that I don't have is the efficiency of a single fin. So let's get that. All right. All right, so this is going to be Q of a single fin over the Q max, which again is if the entire thing were at the base temperature. And so it's going to be H, it's Newton's law of cooling, so it's H times the area of that fin, which again, we've already calculated to be this 0.006 meters squared, times theta B. They told us that we can treat these guys with the tip to be an adiabatic tip. And so from case B on my equation sheet, that's going to be this guy right here. Right? So I've got M T A N H, hyperbolic tangent, M L, and it's the link that you're using is that LF that was given to you in the first place. Okay. HAF theta B. And I think probably what I do need to do is just replace that M. I think I need another piece of paper here. That one. Perfect, yeah, because I think I'm going to run out of room. All right, so this ends up being, the M is going to be, oh gosh, this is going to be square root of H times the perimeter times K times AC times theta B times that hyperbolic tangent times that LF, MLF. Okay. And then I've got H, A, F, theta B. All right. So I'm going to cross out that theta B because I don't really need it. I've got H. The perimeter, I do have to calculate that guy. So I have H. Again, the perimeter, well, it's a rectangular fin, so the perimeter, let's look at it. Let's actually write it up here, what our perimeter is going to be. So our perimeter, all right, well, so it's 2W, clearly, right? So 2 of those. And then it's going to be plus 2T. So it, with this guy right here, that T is so small. You're talking, you have W is 20 millimeters and T is 1/100th of that almost, right? It's 0.182 millimeters. So it's really not going to make that much of a difference as far as the perimeter goes. So you could ignore that 2T if you wanted to. Hopefully I didn't hurt anybody's eardrums. I'm sorry. You could ignore that 2T without it changing anything. I calculated it both ways. It makes about a 1% difference, and not even that. It's like less than 1%. So if you want to put the 2T in there, you can. In fact, just so you're not guessing, I'll put it in there. But you have plus, so 2W plus 2T times K times the cross-sectional area. The cross-sectional area would be W times T. And then we've got the hyperbolic tangent of M times LF. All right, and then you've got H times, and then the area of the fin. So again, we had done this already, and we had already calculated this. So I'm just going to put 0.006, I believe, 0.006. There are 3 of them. There, yeah, 6 meters squared. Right. I guess I do need to calculate. Do need to calculate that M. So maybe I'll draw a little M over here. But this isn't so bad. So M is just the square root of oh, where's my equation sheet? HP over KAC. HP over KAC. And we've defined the perimeter and the cross-sectional area already. So it really is, at this point, it's just plug and chug. So we end up getting an individual fin efficiency of 0.704, so 70.4%. And so now I can plug that guy into my equation up here. And let's see what I end up getting. I end up getting 0.7085. Oh, no, I'm so sorry. Actually, let me fix this guy. It's actually a little bit different, because we took into consideration with the perimeter, we took into consideration the thickness, and that does make a difference. So this ends up being 0.72. And so when I plug that into my efficiency for the entire array, I end up getting, oh darn it, I did it again. I'm so sorry, y'all. 7.2 is for the entire array. So this one ends up, this is 0.70849. So 0.7085, as opposed to what it was before, which was 0.704. So you're really not talking about a huge difference. The 0.04 was if we ignored the 2t right here. And then so when I plug things into the efficiency for the entire array, I end up getting 0.724. Okay, and so just backing on up, now I've got everything I think that I need to get this QC, and I end up getting, there's a lot of work. I've got 31.8 watts. Okay. So hopefully that was helpful. Pretty tedious, but there you go. All right, well, let me know if you have any questions.